Thank you for joining us on the Space Nuts podcast, and thank you to our patrons, who are many in number, who put in a couple of bucks a week, or a month actually, to keep us afloat on the good ship Space Nuts. It's made of wood and it's got a lot of holes in it, and patrons plug those holes for us, so we greatly appreciate it. And if you would like to financially support Space Nuts, it's purely voluntary. It's totally up to you. We are looking at future benefits for patrons, so we'll keep you informed of that. But we're looking at better ways for you to get a bit more bang for your buck. But if you would like to become a patron, certainly visit our website and click on the Support Space Nuts button, the supporter button. SpaceNutsPodcast.com is where you'll find us. SpaceNutsPodcast.com. Okay, Fred, let's move on to our next story. This is the one that's got me super duper excited. There have been methane plumes detected on Enceladus, one of Saturn's moons. This is an ice giant, isn't it? An ice moon, I should say, with what's believed to be oceans underneath. Is that correct?
It is correct, yeah. And the evidence of that, well, there's many pieces of evidence for this structure of a rocky body with a global ocean over the top of it and an ice coating over the top of that. There is good evidence from different sources, but in the case of Enceladus, it's really direct because, of course, the Cassini spacecraft, very early on in the Cassini mission, detected these plumes of ice crystals spurting out of cracks in the ice near Enceladus's south pole. It's really spectacular stuff, and I think it still sends tingles down our spines, just the fact that we've got these geysers of ice spurting out of a body at the other end of the solar system. Quite remarkable stuff.
Did Cassini actually fly through one of those geysers?
I think, yes, several times. There were several fly-throughs, because once they were discovered, which was quite early in the mission scientists, made sure they had several orbits that took it, I think, within 50 kilometers of the surface of Enceladus at some time.
Wow.
And to go through the plumes. And so it was possible for the mass spectrometer equipment on board the spacecraft to sample these things directly, not just to look at the spectrum of the light coming from these ice plumes, but actually fly through and collect bits of ice effectively, which is what they did. Of course, you've got to be careful when you do that. I think they were only really getting to the core of these ice plumes quite late in the mission, because you don't want to risk something big flying past the spacecraft or hitting it if there was a larger chunk. But no, it's from Cassini that we know so much about these ice plumes. Now, I remember when the when the results were released of perhaps the first really careful analysis of what was in them, and it was as you've mentioned, methane plus molecular hydrogen, sometimes called dihydrogen, and carbon dioxide, and those particular molecules were identified. And immediately the conclusion was drawn that they are possibly coming from hydrothermal vents in the bottom of Enceladus's ocean. Now, it's not proof of hydrothermal vents, but it's very strongly indicative of that. And of course, partly because that's what you get from hydrothermal vents on the bottom of Earth's oceans. And that really got people excited. But what wasn't really commented on at the time was the high fraction of that, that set of different molecules that was actually methane, or methane as it's sometimes pronounced. That was higher than expected. And so the question that was asked by the researchers who've done this work, and they come from the University of Arizona and a university in Paris called the Sciences et Lettres University. There you are. Science and arts, I guess, science and literature, science and letters. So the question asked by actually one of the scientists in Arizona, we wanted to know, could Earth-like microbes that eat the dihydrogen and produce methane methane explain the surprisingly large amounts of methane detected by Cassini. Now, the other comment that this person has made is searching for such microbes known as methanogens at Enceladus's seafloor would require extremely challenging deep dive missions that are not in sight for several decades. Well, I can understand that. I think that's a long way down the track. So what they did was they took the better way forward. They built mathematical models to look for different probabilities associated with the different processes, including biological processes that might fit the data. It's a very common way. It's exactly this detective work that we were just talking about. You build a model that lets you test different hypotheses and gives each one a probability as to whether it could be the case. So the thing that they were checking is that on Earth, the hydrothermal activity, which you remember is what happens because you've got cracks on the ocean floor and seawater sinks in, gets circulated through the rocks underneath, which are hot, and then kind of spews up again because it's close to a magma chamber or something like that under the surface, and then comes out into the water again through the hydrothermal vents. Now, methane is actually produced by that itself on Earth. The process itself produces methane, but actually at a quite low rate. And most of the methane we see is from the microorganisms, from the microbes themselves. And so that's the sort of thinking that went into this modelling of the scientists of the Cassini data of the contents of the ice plumes, and what they found was quite interesting because if you assume there's no biology there, you don't get enough methane in your models. But if you throw in microbes into the models, then you do get enough methane.
I understand what you're saying.
Yeah. So what they say, so there's a comment here, a direct quote, which I'll read because it's always nice to do that, from one of the researchers. Yep. Obviously, we are not concluding that life exists in Enceladus's ocean. Rather, we wanted to understand how likely it would be that Enceladus's hydrothermal vents could be habitable to Earth-like microorganisms. And the answer is very likely. The Cassini data tell us, according to our models. And biological methanogenesis, that's the formation of methane, appears to be compatible with the data. In other words, we can't discard the life hypothesis as highly improbable. To reject the life hypothesis, we need more data from future missions. So what it means, Andrew, is that this is still an open question. They haven't ruled it out.
Yeah.
That maybe the methane is speaking of microbial life on the ocean, in the oceans of Enceladus. What an exciting result.
That would be incredible.
Wouldn't
but as you and I have discussed many times, there is likely to be microbial life in the universe, and we just have to find it. And the evidence is stacking up. This is starting to look more and more probable when you try, and it comes down to a mathematical balance. The methane that's coming out of those vents is not sufficient to answer the question as to how it was formed. Something else is contributing. And life is one of those possibilities. Unless, of course, there's another way of producing methane that we haven't thought of that exists inside Enceladus.
That's right. That is right. That's it.
Could be cows. Could be cows.
Yeah. It could also be something.
Sea cows.
Some sort of chemical, some sort of chemistry. Aren't they dugongs? Isn't that right? Dugongs.
Dugongs.
So that's probably what they've got on Enceladus. There might be some kind of chemistry that we just don't see happening, or geochemistry perhaps it is, that we don't see happening on Earth. So, yeah. So it's not proof, but it's really interesting.
Well, the evidence is starting to really lend itself towards possibility, if not probability. But until we are in a position to technologically get there, get down, get in, and get dirty with Enceladus, we're only going to be able to do what they did, which is exciting in itself. But we're going to have to get down under there, and that will be a technological challenge. I mean, this is a really big, thick ice field and deep oceans, and it sounds like an amazing place. It's not the only ice moon in our solar system, though, is it? Europa's another possibility, isn't it?
Europa also has ice plumes, in fact, but that structure seems to be pretty commonplace. 3 of the 4 big moons of Jupiter are thought to have that model. Titan has it around Saturn, possibly Triton, which is one of Neptune's moons, and possibly even Pluto, Andrew. That might have the same structure as well. There is suggestion there might be an ocean, and that's amazing given how Pluto is so cold on its surface, minus 237 or something like that Celsius. It may be one day we discover that there's life on all of these, or in all of these. Who knows? Wouldn't that be extraordinary? But let's just do it one at a time, I think. Enceladus first, the universe next. We're simple-minded folk. We can only do them one at a time.
Yep. I can't walk and chew at the same time. So, yes, let's just stick to one task. But, it is exciting news, and let's hope that it is going to be found that is evidence of some form of life inside the ice moon Enceladus. This is the Space Nuts podcast with Andrew Dunkley and Fred Watson.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.